collaborating. This is part of the fun of this new field that we are all creating together. Okay, so I will talk about this ALeRCE project, which is astronomical broker, as Antares, that is the broker, one of the broker led from in the US and where Gotham is part. And ALeRCE is basically a Chilean-led broker with many institutions in Chile and some collaborators in the US as well. And it's a quite interdisciplinary project. We have computer scientists, many machine learning experts, astronomers, mathematicians, statisticians, and a team of full-time dedicated engineers, software engineers. First, I will talk about alert brokers, the motivation for their existence. So first, the main motivation is, of course, a new generation of large field of view and large collecting area telescopes. Large ETNU, the product of the two telescopes, which will be dominated by the Rubin observatory. That is going to be starting probably 1 or 2 more years. In this talk, I will show data out. I will mention LSST, but also CDF and ATLAS, which can be seen as precursor surveys for LSST. They are smaller telescopes, but with very large fields of view, and they are producing very interesting results today. So these telescopes will produce so much data that it will be a challenge for the community to digest and make sense of it. So this is kind of an invitation for different groups that are able to process large volumes of data to get into this business of time domain astronomy. So in particular in Chile, where ALeRCE is based, there are many follow-up telescopes, survey telescopes that are responsibility for us to use in the most intelligent way. And part of this, because of this, is that we are building a broker to be able to use it in a better fashion. Of course, the star is Rubin. You may have seen this figure before. It's an 8.4 meter telescope with a 3 billion pixel camera, 9 square degrees. And the sky will visit all the sky every 3 nights, and some parts of the sky with more faster cadence. Exposures will be 15 seconds. And after 10 years, you will have a database of almost 40 billion objects. And will produce about 50 terabytes of data per night. As LSST is scanning the sky, it will detect changes in the sky. And these changes will be streamed in alert packets at a rate of about 10 million per night. So if you look at the composition of this alert stream, well, first is 10 million, and it will actually, for every visit, we will get about 10 to 40,000 alerts, with 98% of the alerts being distributed within 1 minute of the observation. Every alert will weigh about 80 kilobytes, with about 20 dedicated to images. And the average data transfer rate that you need to stream this data is about 0.2 gigabit per second. But the important part is the burst, and you will get burst of up to 5 gigabit per second. So it's quite challenging and to distribute this stream to all the world. And because of these constraints, there had to be a selection of a discrete number of broker teams. I will mention later. And this, after 10 years, these alert streams will occupy about 2 petabytes of space, and it's expected to be 90% complete and 95% pure, with a signal-to-noise ratio of about 6. And so for every visit, you will get about 7,000 variable stars, 3,000 solar system objects. If you have 5% contamination, about around 500 bows, 200 supernova, 70 AGN. So for some people, this is the gold mine, and for other people, this is the gold mine. It depends on what your science case. So it's really a multi-objective project. So with this, the future of the time domain ecosystem is something like this. We have survey telescopes streaming data from the Earth, from the ground, from the space, in radio, in actually gravitational waves as well. And this data will be streamed to community brokers that will try to make sense of it. And many layers of brokers. So there will be brokers of brokers, and also telescope manager system that will talk to the follow-up telescopes. And they will do the characterization, the spectroscopy, the observation that will tell you the real nature of these objects. And also brokers will talk to the user community to provide, for example, historical analysis of this data, or more systematic analysis of all the previous data that has been produced. So as I said, the Rubin observatory had to select a finite number of broker teams. And after a call in 2019 and proposals sent in 2020, in 2021, there were 7 brokers selected. Babamul, Antares, and Pitbull in the US, Laser and Pell Think in Europe, in UK, Germany, and France, and ALeRCE in Chile. So what is exactly a broker? I kind of stole this image from Godin, but I put a different character here. And it's basically ingesting a lot of data and facing this data and not being scared of this data. But really, it's not clear what is a broker. I think we are making the definition as we go. So you could say it's a system for filtering or classifying the alert stream, or a system for annotating the alert stream. But there are many questions. Should we just input and output streams? Should we filter or classify based on phenomenology or ontology, astrophysical classes? Should we provide the history of detections? Should we provide direct access to the database, APIs, frontends? And why would anyone build a broker? I think this is the same reason why you build an instrument, because you're opening a new parameter space that you want to explore. What tools should they offer? And I think this depends on the use cases. So I will come back to this. So there's a related interesting question is, why do we need more than one broker? I think this is a question that I hear all the time. And I believe this is because we need diversity. We need diversity to avoid stagnation into one solution. So we know that it tends to happen in technology that you have this winner takes all solution. And I think we should make our biggest effort to avoid this. If you have smaller teams, you can test ideas faster. If you have a very big machine, it's going to be very difficult to change the direction. And I think that we should instead focus on collaboration on standards, benchmark, tutorials, unified tools, and providing more interaction with the user community. For example, some of the workshops that we have organized. Before LSST, we are learning many lessons from precursor service, especially from CTF, and I will mention some of these. So we have been processing with alerts at the rate of around 200, 300,000 per night. And we have seen things like, for example, the schema of the alerts change with time. There is a significant fraction of bogus alerts. Light curve corrections are important. How do you actually translate the alert into a light curve? Working with real data is hard. Sometimes image reference change. There's a lot of satellite contamination, and there will be more in the future. Sometimes the telescope is down, and you have to just wait. In particular, in our case, we have redesigned the database many times based on the experience and the interaction with the users. Should we use SQL or NoSQL? Data releases are very important. These are not contained in the stream, so you need to complement the data with much bigger volumes of data. And interaction with user communities is very important. And of course, we are seeing many cool discoveries. So this is an example of showing the importance of including data releases. So this light curve that you see here is constructed from the alert stream. And if I add the data release information, you see a very different picture. So something similar will happen in LSST, but it will be not as say striking as in LCDF, because in LSST you will get the full history of detections and force photometries. But for CDF is quite important. Okay, so what about use cases? I think that instead of trying to define a broker, we should focus on use cases. So ask the community, what do they need? And then build the tools that are needed to actually accomplish these tasks. And actually, we have asked the science collaborations in LSST in some of these workshops that we are organized, and we are collecting data and making list of things that the science collaboration need. And based on this, we can change our priorities. And as in these 2 years of almost 3 years of brokers, we have seen many developments. Some of the products and services offered are listed here. So the basic input and outputs of the stream, which is based on Kafka, and this is like the must think of a broker. And then you may think also cross-match is very important. APIs, access to the data is very important. Filtering and classifying is important. Providing features, characterizing the light curves are important. The best example is a period. Providing watchlists. What is a watchlist? Is you have a list of objects in the sky, coordinates, and every time there is an alert that is matching one of these sources, you get a notification. You should be able to connect with follow-up infrastructure, with the TOMs that I mentioned before, the target and observation managers. You could do multi-messenger or multi-telescope broken. You can detect outliers and anomalies. You may include or not data releases. And you have to do this in a way that is reproducible and that is useful for the community. So let's talk about classification. Classification can be seen as a kind of filtering or querying based on astrophysical classes. This is an example of the taxonomy, the astrophysical classes used by ALeRCE. So we have 3 branches: transient, stochastic, and periodic. And then within each branch, we subclassify into classes of transients and stochastic and periodic. And you can go on and on classifying sub-branches. We believe that you should not have a very fine taxonomy. You may overfit the classes, but perhaps you should let the community continue classifying downstream and add their favorite source. And this requires very good training sets, both real and simulated. In the case of CDF and ATLAS, and the telescope that we mentioned, there's a lot of data that is real that we can use. And in the case of LSST, this is more difficult to get, and so you have to use more simulated data. But once the survey starts, the interesting part will be combining the simulated data. It can be seen as a kind of a pre-training with real data. And this is a community effort. And actually, Golem has been leading some of these simulations. There are many models in the community based on different kinds of data. For example, you can use the first detection to classify, or you can use images, or you can do classification in real time as the source evolves. You can work with light curves, or perhaps just with cross matches. There are many different types of classifiers, and some of them are shown here. So the LSST classifier, supernova from Think, the LSST light classifier, Rapid that is used by Antares, and Sherlock that is used by LSST. And there are more classifiers. So one warning here, this article in MIT Technology Review that was very important, I think, and show that we have to be very careful what we're doing. there were, as it says here, hundreds of AI tools built to catch COVID, and none of them helped. So why did this happen? And they say, well, there were problems with data sets that were they call Frankenstein data sets. So we have to be very careful when we curate our training sets, how they are balanced and how much we can trust them. Also, the skills. I mean, we have to really work in interdisciplinary things and work with the experts on each topic. So the astronomers that know exactly which data they can trust, how to interpret it. Machine learning experts that tell you how to best train this and make it generalize well. And of course, perhaps the most important is much more rewarded to publish a paper than to put something in production. And I think this is very, very important. Maybe you have seen this in NCSA, I don't know. So putting things in production is very hard, very, very hard. Okay, so now we switch to the ALeRCE broker. So ALeRCE, as Gordon said, is a tree that is kind of very similar to the redwood trees in the US, and also in the Pacific coast. And actually, recently there was one ALeRCE tree that is supposed to be more than 5,000 years old. So it may be the oldest tree in the world. But ALeRCE is a Chilean-led initiative to build a community broker for LSST and other large NNU survey telescopes. And our main goals is to fast classification of transients, variable stars, and active galactic nuclei, to enable the exploration and systematic study of variable objects, connect survey and follow-up resources, and be flexible to adapt, because we know that this area is going to be changing very fast. These are some pictures from our collaboration in 2018. We started a meeting in south of Chile, in 2019 in Chile, in La Serena. This is Valdivia, La Serena, Santiago, Concepción. This is pandemic. We had tutorials online, and 2021 Santiago. So you see the project has been growing, getting more diverse, and it's been quite fun to work on this, I would say. The scientific questions are many, but you can group them in 4 main topics: transients, explosions of stars, variable stars, all the variable persistent sources that are with stellar origin, AGNs. You can detect, not only detect an AGN, but also detect changes in their behavior, like changes state AGNs, do regression mapping, etc. And solar system objects. This is one of the main reasons for Rubin to be built, and so we cannot ignore it. So the core of ALeRCE is its pipeline that is shown with its basic structure here. So as the alert stream arrives, what we do is to have processes that are started in parallel, using Kubernetes and Dockers in a modular way. So we store this data in the cloud in Amazon. We're switching to hybrid operations. We do cross matches with public catalogs, and then we trigger 2 classifiers: the stamp-based classifier with the images. This is for quick and coarse classification, and the light curve classifier that is more precise with more classes, and this requires pre-processing of the light curve computation of features. And this also enables the classification of and detection of outliers. So we did some tests at LSST level, and we were able to achieve decent execution times per alert, so less than 1 second per step, and the time from arrival to end, it could be tens of seconds. Of course, this depends on how many machines you put into this, and we will see how this works in real life with the real data. And the 2 classifiers that we have are shown here. It's their confusion matrices. So first, the stamp-based classifier. This is the quick and dirty classifier for the first images. You get the first triplet of images of an alert, and you also use some contextual information, and you can do quite decent classification into AGN, supernova, Bible star, asteroid, and bogus classes. With this, we can report very, very young supernova with just one detection, and it has been quite successful. We have been quite successful doing this in reporting supernova to the community. Then the light curve-based classifier, that is uses the light curve information with objects that have at least 6 detections in a given band. So you have to wait a little bit. And this is as it says, the name says, it's a hierarchical classifier, and uses a balanced random forest behind. We have tried many methods, more modern methods, and still this is the best performing so far. So what are the hierarchies that we use is transients, stochastics, and periodics, and within each branch we subclassify, and this is the final confusion matrix you can see here. Apart from these classifiers, then you can access the data. Some of the tools that we have is, for example, the ALeRCE Explorer, where you can actually visualize. For example, here you do a quick query of type 2 supernova, and you get a list, and you can see the light curve, some contextual information, machine learning probabilities, image times, adding images, and cross-match information, changing the distance, for example, the redshift. And you can switch between sources very easily. And this has been super tested because you use it every day to look at the candidates. Then we have the Supernova Hunter. The Supernova Hunter is a tool that allows us to visualize the most recent and best supernova candidates and visually classify them, and then use this information to report to the community. So adding a human in the loop to the machine learning stage. These candidates are all enriched with host galaxy information. So we manually select the host galaxy, and we're actually using this data, as I will show later, how to identify the host galaxies. And this information is also included when we report to TNS. We have a watch list, as I mentioned before. So you have a list of coordinates in the sky, and you want to get notifications every time there is an alert that matches the position that you entered. And you can explore it. It's connected to the Explorer, and see the light curve. As I mentioned, we have many features that are computed for every light curve. So in total, it's 174 today. And these different features come from different sources, but the most important source is our own features. And as you may remember, we have a hierarchical classifier. So first we classify into 3 classes, and then within each class we subclassify. And the most important, the top 5 features per classifier are the following. So for the transient, stochastic, and periodic, top classifier is all wise colors, star galaxy information, the fraction of positive values, and something related to how the object is rising. Within the transient branch, actually, the top 4 are related to the supernova analytic fit. So it's really the shape of the supernova light curve and the color at maximum. For stochastic, is mostly colors from all wise combined with CDF colors and star galaxy separation score. And for the periodic, of course, the period is the main feature, but also colors in between CDF and all wise. So as you can see, all wise is quite important for this classification. So I mentioned before the data releases, the importance of data releases, and this is an example of how we are using this. We have a light curve from CDF coming from the stream that was identified as a potential outlier according to one of our algorithms. So we explore this light curve, and when we see the data release, we see something completely different. So if you really want to make sure that what you're reporting is relevant, you should enrich with the data release. We have many notebooks, and you can find them in our GitHub repositories. And you have notebooks for AGN science, for asteroids, for supernova, for variable stars, for machine learning, and miscellaneous things that we are always adding. So we have a large user community. I think most of them are coming because of the reports that we do to TNS. So we have counted people from 125 countries, more than 6,000 users. And as I said, this I think is mostly because we are reporting many candidates to TNS. So we become the third biggest source of TNS reports, and the third source with more classified supernova. So the supernova that we are reporting are being classified, and so this is good sign that they are actually real. And this is the distribution of these sources. And if you want to follow the applications, you can follow this Twitter account, ALeRCE Discover. We have APIs and clients. So this is the main API where you can query objects, you can query the light curve information, statistics about the light curve. You can query objects by probabilities in the taxonomy that we have. And you can query the classifier information, and you can query features. We also have an API for the data release, so you can query the light curve from the data release. And we have a client that uses the API to make your life easier accessing this information. All brokers are basically having their own APIs and clients in different ways. These are examples of how you use the client. This is in a Jupyter notebook. You query objects asking for a given classifier with a given class with certain probabilities, with a given number of detections, and how you sort this data and output as a data frame, just simple pandas. You can also use VO tables. This is an example of directly querying the database in PostgreSQL. This is what we're using for CDF today. And you can see all the details in our GitHub repository. Some current developments. We have been working for a long time on outliers. We have tested many outliers methods. And what we have found is that the best outlier method, there's not one single best outlier method. It depends on which branch of the taxonomy you are. So for transients, you have one outlier method that works better, for stochastic object another, and for periodic another. And this is an interesting example. This was detected as an outlier. And this is not really an unknown type of object. This is a microlensing event. But it was detected as an anomaly because it was not in the taxonomy. So actually, this is able to detect classes that were not represented there. We're also able to detect things that change their behavior. So this is an AGN that changed to the change state. And for this, we're using variational autoencoders. This work led by Paula Sanchez Saez and Manuel Perez. We're doing our first attention-based classifiers, so transformers. The nice thing about these attention-based classifiers is that you can ask the model, what did the model look? What did you look for to classify? So what we're seeing is that in supernova, for example, the early light curve is very important. It's much more important than the information after maximum. We also have methods to do full inference of the posterior in an approximated way, but in real time. So you can do thousands of posteriors per second using something called amortized variational inference. Basically, you train a neural network that predicts the parameters of the posterior that you have parameterized before, and you train it with real data. We have we're working on automatic identification of galaxies. So basically, what we do, we have images centered in the different candidates. We change the representation of this image into multi-resolution images. We feed into neural network, and the neural network can predict the most likely, or the position that the neural network believes is the center of the galaxy. And the nice thing about this method is that it gives fewer catastrophic errors than other methods. Although it's less precise, it doesn't give you the very accurate position, it gives you fewer catastrophic errors, and this translates into fewer let's say, smaller errors in the redshift determination. So this is the experiments that we are doing with redshifts. So we search for the closest cross matches in Sloan in the test set, and we can see that we can report how many matches we found and how many big errors we found, and that we found that our method is actually better, especially with larger galaxies. So you can handle small and large galaxies. We're also using this idea of multi-resolution to try to address one big problem that is coming with this LSST. So CDF, this is the image stamp size. It's decent size, it's 61 arc second, but LSST is going to be tiny. So you get fewer context to do the classification. For example, you barely see this galaxy. You have to look at in a catalog. Or, for example, you could use a multi-resolution image. And this also helps you classifying satellites that are going to be like abundant in the future. And so we are using this multi-scale stamp classification that is also in preparation. Something else we're doing is, in collaboration with another broker, ALeRCE, is actually combine ATLAS and CDF data. So why combine these two surveys? As you may have, if you remember from previous slides, ATLAS is quite prolific source of supernova today. And if you combine both sources of data, you get much better characterization of the light curves. So, and actually from a few weeks ago, we have the first examples where we actually have data from both surveys. So this is a CVNOVA, and you see how you have data from CDF and from ATLAS, and it gives you a much nicer picture of what this really is. And so you see this characteristic like of a CVNOVA. And this is that type 1a supernova. In this case, ATLAS really gives you a much better view of the rise of the supernova. And in some cases, you have data from ATLAS that is before CDF and vice versa. So it also allows you to do faster classification. So as we move to ATLAS, we're kind of stepping between CDF and LSST. So we have to switch to a different type of database system. So using MongoDB. I don't know how this will, if this will change or not, but so far this is our bet. And because ATLAS actually produces many more alerts, sometimes 1 million alerts per night. So you need a different kind of distributed database system. And our intention is to continue in the same path towards better Rubin. In the end, the infrastructure for Rubin will be have this kind of structure. You have a speed layer for the online processing. This is the pipeline. You have all the offline, the massive data processing that you need to train the models or do systematic analysis. And you have the layer that serves the users. And we're using tools in the cloud and on-premise. Basically, we are inclining to move all the pipeline to more on-premise infrastructure and services to the community and things that are bursty to the cloud. See, these are some examples of the tests we have done for Rubin in terms of alert ingestion, in terms of processing and computing features using Kubernetes, in terms of insertions in the database and spatial queries in the database. So finally, I will talk about the science that we're doing with ALeRCE. So first, some examples of early supernova detections. This slide copy is interesting because it shows detections in CDF and in ATLAS, orange and cyan. And in this case, you see a supernova that was detected almost simultaneously with ATLAS and CDF. So the fact that we had two detections made us more confident about this object. And so we could send an astronaut saying that, okay, we combine both telescopes to detect this candidate and get then very early spectral time series. So in this case, 14 days before maximum, sometimes before that. And in general, we're using TO time from Gemini, that is led by Giuliano Pignata, and his postdoc Raya Dastidar, also using other telescopes, and also some telescopes in Caucasus Mountain Observatory. They actually sent already 18 classifications the same night to TNS. And this is one example. So supernova 2021 PC, we got 2 detections from CDF within 50 minutes. And 12 hours later, we had a spectrum saying that this was a type 1a supernova. And the third detection from CDF came only 47 hours later. Another example, we have discovery, and 30 minutes later, a second CDF detection. 8 hours later, we submit a TNS report. 18 hours later, from discovery, we have the first spectrum. And the third detection comes only 46 hours. So if you really want early spectroscopic follow-up, you really need to combine the first 1 or 2 points on the light curve. And for example, what we're seeing is very high silicon velocities, the highest measured so far. As far as I know, this is led by a student of Giuliano Pignata, is Jonathan Pineda. We're also doing the physical characterization, uses TARDIS, model that actually do all the radiative transfer, and for the same object as shown before. Another interesting thing is we're using CDF and ATLAS light curves for type 2 supernova in this case to get physical parameters and to show that this actually can be trusted. And physical parameters, I mean energy of explosion, the radius of the circumstellar material that happens to be important, the mass, explosion time, and the redshift. So in this case, we didn't have redshift, and then we tested whether you can recover the same redshift as the one you get from the galaxy, and actually it works. So this is the redshift inferred from the light curve for spectroscopic redshifts of the host. When you compare to photometric redshifts, this correlation is lost. And then also discovering changing look AGN with very simple method. In this case, Elena Lopez Navas, what she did is basically use a catalog of type 2 AGN that supposedly don't vary, and then search for AGN detected in the CDF stream and classify as AGN by ALeRCE. And in this case, she had a sample, and with 6 objects that she observed, she found 4 changing state AGN, changing look AGN. So this is quite efficient way of detecting changing look AGN. So finally, to summarize, ALeRCE is a cloud-based broker based in Amazon that is ingesting CDF alerts since 2019. Is now ingesting ATLAS since a few weeks ago, and was selected as community broker for LSST in 2021. We have a living catalog of objects, annotated and classified streams, API clients, interfaces like CDF Explorer, Supernova Hunter, watchlist, connected also to TOM toolkits. We're actually the first broker to publicly classify the CDF alert stream and send it to the community. We're first to use image stamps and light curves to classify real objects with astrophysical taxonomy, to include data releases, and now to ingest the ATLAS stream. We're actually reporting the broker that report most TNS candidates and associated classifications. In terms of scientific results, we are getting many young supernova characterized, changing look AGN and outliers, and in progress many things: more outlier detection, automatic galaxy identification, automatic satellite detection, attention-based classification. This actually may be the one that beats the random forest. Real-time parameter estimation, classification with elastic. Ask Golam about elastic. It's a big effort to do simulated light curve for LSST. migration to MongoDB, and scaling to Rubin. So with this, I finish, and here are some links and publications. Thank you.
Tremendous. Thank you so much, Francisco. That was a wonderful talk. If we have any questions for Francisco, please use the raise hand feature. I see Kostya has went up straight away, so let's start with you, Kostya.
Yeah, thank you. Hello, very nice talk. Thank you. It was super exciting and super interesting. So I have a lot of questions, but I will start with the first one, coming back to the very beginning of your talk, when you mentioned about one broker question. So it is actually the question I also ask any broker team, and I have some, so you answered it, but I have some relevant question. So do you believe that separation between LSST responsibility and broker's responsibility is done right? So for example, every broker is doing a lot of things the same way. Yes, for example, catalog cross-matching or light curve photometric correction, they're done in a very similar way. So so I understand that we can change nothing in this place, yes, but we can discuss how it could be better in the future for future. So what do you think?
I agree with you, and I think the cross-matching, in particular cross-matching, is the same. So this should be shared. Then the machine learning classification, and this, I think this is where you can add the most diversity and more ideas. It's a very fast evolving field. So I think, and I have mentioned this, but when someone has to do it, and it's a lot of work, and we're all busy. But if we put together, let's say, one broker that only does cross-matching and just serves the different brokers, this is one way of kind of unifying some certain aspects of the brokering system, but not all the aspects. If you unify everything, then I think you're stuck. It's going to be very difficult to move.
Yeah, thank you so much for answering. Yeah.
I'll
also quickly mention that we have a time domain workshop in Alberta, July 25th to 29th, which has a session on Wednesday called Brokers and the Alert Stream for exactly this kind of discussion. People. Yeah. Alex Galliano.
Hey, wonderful talk, Francisco. I just wanted to ask if you could elaborate a bit more on the attention work that you're exploring right now.
Yeah. Yeah, so in attention, this you can see the details in archive. It's Oscar Pimentel is the first author, and basically this new architecture is called transformer, which is based kind of on queries and keys and values to query for information, and then with a neural network in the end classify. But the nice thing is that the way this is built, it allows you to interpret more easily. It's hard to understand how this works. If you read this paper, the section where this is explained is quite dense, but it's different to CNNs and RNNs. Is this idea of the using of the transformers. I don't think I can explain it quickly. This is it needs more time for me to explain.
Sure.
But I read this many times, and it's the first time I see that we are beating the random forest. I can say that, and only for supernova. So this is just based on supernova.
Fair enough. Okay, thank you.
Yeah. So, but basically, you train everything here with a neural network. How do you define values? How do you find keys? How do you find the queries? So I recommend you to go to this paper.
Will do. Great.
Deep. Deep, if you're unmuted, we can't actually hear you. Still not up. While Deep is figuring out audio issues, maybe I can ask a quick question. I noticed that you talked about this changing look AGN, and you were using an autoencoder. There's certainly a lot of people at UAUC, in particular UA Shen and Jun Liu, who really care about AGN and changing look AGN. And I was wondering whether you have a decoder to go with it to sort of simulate changing look AGN light curves.
I think you could, because I mean, you in the end, what you do is you simulate based on this latent space.
Yeah.
So you could create a. I recommend that you talk to Paula Sanchez.
Yeah.
Says, yeah, it should be very easy to do simulated light curves. Of course, simulated light curves are shown here in red.
Yep.
They're not perfect. Real data is much more complicated. But in this case, it was a useful method for the purpose of identifying this changing look AGN.
Very cool. Deep, I think you fixed your audio.
Can you hear me now?
Yes.
Yes.
Okay, perfect. Yeah, thanks, Francisco. This was an amazing talk. So I had a couple of questions. The first one is, so because you have so many of these classification algorithms, I'm wondering if there are discrepancies in real time or otherwise. I'm wondering, how do you go about that, and if any post-processing step is dependent on them. I'm just wondering, how do you go about if multiple classifiers end up giving conflicting results?
Yeah, I mean, this inevitably will happen. I can show you some comparison between the two classifiers in here. So what we tested is, let's say, whether the stamp-based classifier was consistent with the light curve-based classifier, and we found that mostly they are consistent. So things that were classified as supernova by the stamp classifier were also classified as supernova by the light curve classifier. AGNs were classified as either AGN, rays, or quasar, but some superluminous supernova, which is wrong. And variable stars also were consistent, except for blazars. Sometimes we had contamination there. And yeah, no asteroids or bubbles. So they're roughly consistent. However, there's also the consistency with time. Let's say you have the light curve that is being built, and the classification can change. We haven't done a deep analysis of this, but I have seen some examples where this happens. And it's natural, and as the same happens to us when you look at the light curve, you're not sure, and then you get, for example, type 1a, you may see the secondary maximum, and you say, okay, it was not a type 1bc, for example. So yeah, man, that's all I can say. I don't know if this answers your question.
No, thank you. Yeah, I think that does. I mean, I know that this can be a very difficult problem overall, and I was just curious that how are you going about it?
Yeah, I mean, one thing we are not doing is keeping the historic classifications of the objects, because it will be that's too heavy. But I think another broker is doing, Ampel is doing that.
Can I ask a follow-up, or rather not quite a follow-up, but a slightly different one on one of your classifiers, that is the real-time posterior estimation. And I'm wondering if you could give some details about that bit, and in particular, after you have trained it, how robust is it to the noise properties of the instrument?
Yes. So the way you train this is using something called the evidence lower bound. So you have the observations, and you have the simulated observations, let's say, and really what you're training is this network that, given the light curve, predicts, let's say, 6 parameters, which are the parameters that are used to parameterize the posterior. This is the important part. And you can include full covariance matrix or more complicated representation of the posterior. But really what you train is this network that predicts the parameters of the posterior. And how well it generalizes, the experiments we are doing so far are based on type 1a supernova. And yes, so if you use, for example, the ALeRCE stream, and then suddenly you include force photometry light curves, this may not work so well. So you have to readjust depending on the source of data. So you need to do some domain adaptation. You cannot just use it for any telescope it requires this adaptation.
Yep. Thank you so much.
I see Kostya's hand, but just in case any of the students want to ask a question, since she's already gone once, I just want to make sure that we get to you as well. If not, Kostya, let's finish up with you.
Well, I also have a question, but we can go.
Sure. Sorry, Felipe, I didn't see your hand up there. I thought it was the clap icon.
It looked like clapping, always a part. So Francisco, so I have a question about the, in terms of the road that you have to take to get here, and you have a slide when you talk about how you have been evolving in terms of the database requirements and how you started with for the Postgres and then you went to MongoDB. I was wondering if you can, tell us a little bit about the background of when did you learn, what doesn't work, what were the struggles, and how you end up to the current paradigm of the databases that you're using.
Yeah. So I'm not expert on this, and so the engineering team is leading these decisions. However, what I can say so far is that it was necessary to move away from Postgre if it was not distributed. Otherwise, the rate of queries will not just make it crash. And then the other things that I'm still a bit slightly worried about how much space this will take. It can take a lot of space using this representation with, let's say, JSON files and so on, and although they are binaries. So we may have to sacrifice some data and just not include everything. So this is what has surprised me more is the amount of space that this uses. We also tried at some point Cassandra, and it's also a valid database. In the end, we stay with Mongo because CDF is using Mongo. So it's more tested with a database of billions of rows.
Well, thanks.
Yeah, but maybe wasn't very useful, my answer.
Kostya and Deep, and then I think we should wrap up.
Yeah, I'll try to be short. About host center prediction, what have you used for training set? Simulating data real, and if it was real, what is the ground truth?
Yes, remember that I mentioned that we are submitting the reports to DNS with a manual identification of the host. So we do for all the almost 15 sources that we are submitting, we manually identify the host. So this is our training set. By the way, this is work that I've been collaborating with Alex on this subject. Alex Agliano, who's here.
Yeah, in fact, I'm really hoping that paper is done soon because we have a version of Ghost in the easy system as well as Antares, and I'm fairly agnostic about using tools that other people build. Whatever is the best thing for the job.
Yeah, I wish I had this knowledge before, but the return to presentiality was quite stressful. Yeah.
Cool. And Deep, I think you said you had one more question.
Yep. Yeah, I saw Kafka streams in one of your slides, and I'm assuming that probably you're using that for some kind of an aggregation on your Kafka streams. But in my knowledge, so the two popular technologies that I've heard are Kafka streams and KSQL DB, and I'm wondering that why do you choose Kafka streams over KSQL DB?
Basically, because CDF is streaming with Kafka, and LSST will also apparently will do it with Kafka. So.
Oh, I see. Okay, but I mean, so KSQL DB is also another aggregator technology, but I believe Kafka streams is the more popular one, and that's why the choice.
Yeah, it's a border condition for us. Yeah, but yeah, I know maybe it's good to ask the LSST team about this. If you can convince them and you think it's better, yeah.
I mean, I think they're going to stick with Kafka. They might be using a schema registry, but
The schema registry is very useful. Yeah.
No, I certainly don't think like one is better than the other. I was just trying to gauge, which one is a better choice than and why. But yeah, anyway, that can be a
We haven't
conversation
tested
for later.
We haven't tested other alternatives.
yeah, I think in a lot of these cases, it's there's lots of alternatives, but it's nice to have something that works and just get on with it. Just start working. Well, anyway, thank you so much, Francisco, for a really wonderful talk. And Srini, thank you for recording that talk. I hope you'll send Francisco a copy as well as share that widely. We should put it up on our YouTube channel. That was really wonderful. I just wanted to remind you all that we have a CAP seminar next week, and this is a seminar from two of our current CAPS fellows. Patrick ALeRCE will be talking about his work on classifying the young supernova experiments first data release photometrically and preparing that entire data release. And Colin Burke will be telling us about his work on changing to KGN and dwarf AGN as well. So hope we will see you all in person at NCSA in 2100. Again at 12 o'clock next Friday, which is June 3rd. There will be plenty of pizza, so you can hopefully make the trip to NCSA and it'll be rewarded with some tasty treats. We will see you all then. Bye-bye.
Bye. Thank you.
Francisco. Bye.
Bye. Thank you, Francisco.